In the next section, what we're going to do is we're going to start working with finding the area under a curve. And eventually what we're going to do is we're going to tie in area under a curve and how it relates to integration. Actually, there's an integration process. It's called finding a definite integral that allows us to find the exact area under a curve, not approximate or get real close or have a limiting process where we're super close, but it's actually an exact process, and it's called the fundamental theorem of calculus. It's one of the top 10 math discoveries of all time. I can't remember which number it is, but it's a pretty big concept. Before we can tie in area under a curve to integration, what we're first going to do is we're going to estimate finding the area under a curve using rectangular approximations. A lot of times these are called the Riemann sums, sort of. So what LRAM stands for is what's called a left rectangular approximation method. RRAM stands for right rectangular approximation method, and the MRAM stands for midpoint rectangular approximation method. And then there's also going to be a trapezoidal one as well. Over the last few years, there have been computer programs and calculator programs that have been written that do this. I have them, and if you want them, you're certainly welcome to connect my calculator with the link, and I can upload it for you. The only thing is they're really not helpful because on the AP exam, you will be asked to do this. But it'll either be without a calculator, or if you get to use a calculator, they rig it so that the program isn't helpful. And we'll discuss that more as we get into the process. But what we're going to do right now is we're just going to take a very easy curve to work with, which is a parabola. I'm going to write it a little bigger over here. F of x equals x squared plus 1. And I've already graphed it here, and I've graphed it on the interval from 0 to 2. And we call this from A to B. So I've got my graph of my parabola, and in green you can see the area under the curve. And to demonstrate the area problem, what we're going to do is we are going to chop that region into rectangles because we know how to find the area of rectangles. We just do length times width, or we do base times height. We are going to divide it into what we would call right rectangular regions. What I mean is we're going to go all the way to the right of the graph. We're going to head up till we hit the curve, and then we're going to go over. And we're going to repeat that all the way on down here, starting at the right, heading over, going down, hitting at the right, heading over, going down. And these points where we hit the curve are going to be important. All right, so we are going to do what's called a right rectangular approximation method. Notice it's not going to probably be a very good approximation because I've got a lot of white stuff up there that's going to be included in my rectangles, but that is not shaded in green. But the process behind it is this. We can get the area of each of these rectangles. I'm going to call them area 1, area 2, area 3, and area 4. And to get their area, what we do is we use the area of a rectangle. And to get area of the rectangle, we need its base and we need its height. Well, let's go up here and discuss how you get those. If your interval is from 0 to 2, that means it's 2 in length. You would just do what the book says, you subtract them, and that gives you how long of an interval you have. And we are going to chop this into 4 rectangles. So if I take the length of 2 and divide it into 4 pieces, each would be a half. That's what I would do. The book gives this formula for it, and yes, it works, but really what we're saying is the base of one of these rectangles would be the whole thing, which is 2 divided into 4 pieces, which means the base length on each of these is a half, and a half. And what we call this base length with our calculators is change in x. So we've got change in x is a half, change in x is a half, change in x is a half, change in x is a half. What they'll often do on the AP exam is they won't have those be consistent. And what that does is whatever computer or calculator program you're trying to cheat with, it won't work. So we really do need to know the process for this. So I have my 4 rectangles, and each one has a base of a half, or what we would say along here is a change in the x-axis. So in mine up there, my delta x which is the base of the rectangle, is a half, and you can see it on the picture. So in order for me to get the height of every rectangle, what I do is I've got the height of each rectangle is that high, and that's where this dot hits the curve. Same thing here. The height of this rectangle, it's this high, and that's where the dot is hitting the curve. And if you'll notice, this curve is f of x, and so this point right here would be the y value at a half, so we'd say that's f of a half. Likewise right here, the height of this rectangle is f of 1. And in general, really what this is f of your first x, second x, third x, fourth x, and we call that f of x of I. So there's a lot of notation in this section that really I wouldn't memorize, and I wouldn't get too stressed out if you don't really get the notation, because basically what we're going to be doing is finding the areas of rectangles, and if you just keep that in the back of your head, you'll be very successful. So let's go to the next page. So what I'm going to do here is we are going to actually go find what our approximate area is using mine. So again, I've just re-put this picture on here. So I've got my 4 rectangles, and I've got each one of them that has a base that we're calling delta x, and in this case it's a half. Remember, you kind of know what I did is, again, I took the length of the whole interval, which was 2, and I divided it into 4 pieces. If they told me to use 6 rectangles, I'd take that length of 2 and divide it into 6 pieces. Don't memorize b minus a over n. That's not helpful. Just how long is the base. And then the height of each one is my x value there. So, for example, let's do this. The area of rectangle number 3, which would be its base, which is a half, or delta x, times its height, which is the y value right there on the curve. That's f of 1.5. And how do I get f of 1.5? I remember that my function is x squared plus 1. So I just put 1.5 in there, square it, add 1, and that'll give me the height of the rectangle right there. So then, if I know how to find the area of one of them, I can simply add them all up to get an approximate for the region. And when we sum stuff up, this is our summation symbol. This is just saying add up. This is really base times height. It's basically just saying add up all those rectangles, which becomes base of 1 plus base of 2 plus base of 3 plus base of 4, the area of each of those rectangles, which, let's go actually calculate it. For each one of them, they have a base of a half. So for rectangle number 1, I would do 1/2 of f of 0.5, because that's the height right there. Then for the next one, I would do 1/2 of f of 1. And then I do base times the height of the next one, plus last one right here, that would be f of 2, which would be 2 squared plus 1, which would be 5, technically, when I put it in, but we say that's 1/2 of f of 2. Now, I've already gone to my calculator, which I'm going to allow you to use them and use the table version. We'll talk about the proper use of a calculator in this section later on. But what I'd like you to do is, if you could, go to your calculator, of which I've already screenshot some stuff in, enter the curve. You can hit graph so you can see it. I actually set my calculator to calculate the area under the curve. You don't know how to do that yet, and I'm not going to tell you how to do that yet. And I set my window so I could go from 0 to 3 by 1s, because it said to go from 0 to 2, so I just went a little past it. And then I went from 0 to 6, just to get a good viewing window there so I could see the whole curve nicely. Anyway, go to your table and make sure you have it set to ask. And we are going to go grab off our values here. Notice I'm not including the first one, because that one, I'm going to go back here. We're sticking to the right here. It's hitting here, 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 here. So when we grab those values off the table, again, you should have that entered. I'm going to go do that. F of a half is 1.25, so that'd be 1/2 of 1.25. f of 1 I can do in my head because the curve is x squared plus 1, so that would be 1/2 of 2. And then 1/2 of f of 1.5 is 3.25. Again, you can just go ahead and use your calculator. F of 2 is 5. So basically what I'm doing is adding up all the rectangles 1/2 times the value of the function at the right endpoints. And when you work that all out, I believe you get about 5.75. And that's what those 4 rectangles add up to. Then it says, is this an underestimate or an overestimate? Well, you can see that I've got way too much included there. I've got a big overestimate. And the reason why is because the rectangles go above the curve. And we'll talk about how you know that later without graphing. So now what we're going to do is, well, how would we do one that does the underestimate? And what we would do for that is we would go and make what we call left rectangular approximations for this one, which means I'm going to go to the left and hit and go over, go to the left, hit and go over, go up, hit and go over. Notice I started on the left and I am still making 1, 2, 3, 4 rectangles, but these are called left approximations because my left endpoint is hitting. So moving that on to the next page. I'm going to have to go into 2 videos here. We'll go to the next page. So when we hit on the left, again, we have 1, 2, 3, 4 rectangles that we are going to be adding up, and this is called a left endpoint estimation. In this case, it's an underestimate. It doesn't mean it's always an underestimate on the right, though. It has to do with how the function is going up or going down. Because when you have a function that's actually decreasing and you do a left endpoint approximation, sorry, it's not very good here. But anyway, when it's decreasing and you do a left endpoint approximation, it ends up being, I gotta fix that. Make one that's going a little steeper and a little bit more drastically so we can see it. So when we stick to the left here and we go over, down, suppose we're chopping it into, let's pretend, 3, not good enough. You can see here what I've got is an overestimate because the rectangles go outside or above the curve a little bit. So the function, whether it's giving us increasing, decreasing, will determine whether we get an over or an underestimate. The way I told kids to remember it last year that kind of helped is really just to remember one word. And I said, remember real. On a right rectangular approximation, if it's an increasing function, it's an overestimate. And if you can just remember that one, all the other ones can fall out from it logically. Because if a right on an increasing function is an overestimate, then a right rectangular on a decreasing would be an underestimate. Likewise, the left on an increasing would be an underestimate, and the left on the decreasing would be an overestimate. And if you can remember this one, you can kind of get the other 4 for free. So let's see if I can get this calculated here in the next minute and a half. So here's the calculations for finding the area of these 4 rectangles. Notice again, I've got the same delta x, it's a half. So what I'm doing is base times height, base times height, base times height, base times height. And in this case, you know, I screenshot this off of something where they kept them as fractions, but you could use the decimal versions off your graphing calculator table as well. But notice because I'm sticking to the left here, I'm never using this endpoint. I'm never using f of 2. I started way at the left with f of 0 as the height of the first rectangle. F of a half is the height of the next one. F of 1 is the height of the third one. So when you stick to the left, notice this last one over here gets left off. And when you calculate that out, you get a 3.75. So down here, it says, I'm going to start a new video because I've only got a half a minute left. So I'm going to stop this one and I'll pick it up from right here and we'll talk about midpoint approximation method. And then maybe I'll do one on the homework so you can see the format that I want these done on. So I'm going to make a new video and I'll post that as well.